All right, let's get started. Everybody ready? Yeah? No? Yes? Are we ready? I can wait, but not too long. You ready? Okay, cool. Anybody got any questions before we get back to calculations and all that fun stuff? Homework questions, anything like that?
I have a question.
Okay.
I think it's number 11 though.
Okay. On which homework assignment?
Chapter 3.
Chapter 3. Homework? Number, you think it's 11-ish? Okay. Let's see. This one?
Yes.
Okay. So histogram on the right determine whether the mean is greater than, less than, or approximately equal to the median. Justify your answer. So this distribution has what shape? It's definitely skewed, and it's skewed to the, remember the skew follows the tail? So this is skewed to the right. What's going to happen to the mean versus the median here?
The mean is going to be skewed to the
Yeah,
side.
yeah. So the mean's going to get dragged towards the tail, towards the skewness. So the mean's going to get dragged up. So the mean should be bigger than the median. And so you would say, where would that be? The mean is going to exceed the median because the histogram is skewed but not left. The mean is going to exceed the median because the histogram is skewed right. So it'd be that one, I think. Yeah? So not only do you have to figure out which one's bigger than the other, but you also have to pay attention to make sure you get the skew correct as well, and I think that's correct. Okay. Yeah? Yeah. Any other questions about the homework? Yeah?
I had a question. What does the I stand for in XI again?
It's an index, so it just means like, here, let me give you an example. It's just, where's the website on my screen? Oh, here we go. So you're just gonna, it's like, so for, like, let's say you have student 1, right? And then you're recording something about them. So this would be X1. For student 2, you'd have X2 all the way up to, student I would be observation XI up to like student N would be XN. And so when they're talking about something like this, like this subscript is just the indice, but it's basically just it's just a placeholder for each number of observation. It doesn't actually mean, it doesn't have a practical meaning except for it in the actual technical notation. We're supposed to tell you where I goes from and to. So I would want to say that I goes from 1 to N. So it starts at X. That means it's going to be X1 plus X2 plus all the way up to XN. Yeah. Okay.
What's the E? Sorry.
This is a sigma, and that's a capital sigma. It's a Greek letter, and it basically means sum. It means add it all up, right? So anytime you see that, that means you're going to add up a bunch of junk. Okay? Yeah? So, all right. Any other questions? Great questions. Anything else? Ooh, that looks weird. Don't like that. I did put out, I went ahead and put out the practice test. So our first exam is coming up next Thursday. So that'll give you plenty of time to take a look at that as you're also working on your homework. It's in the practice exams folder, so you can find it there. It'll give, and if you're, so for people, I've had some people who were worried about like what the test was going to look like or whatever. This will give you a good idea of what the exam is going to look like. So gives you some problems. And it all comes out of chapters 1 through 4. Yeah.
So we can still bring like 1-page notes, right?
Sure. Yeah. You may. You may bring a page of notes with you to take your exam.
It's just one-sided, right? Not front and back. For the page.
For the test, or the notes is one-sided, front side only. Front side only. One page.
So it could be front and
A page is not front and back.
bring a magnifying glass?
In what book? You can do whatever you want on that page.
Really small font, you get more stuff on there.
Mm-hmm. Sure. Why not? Okay. Any other questions? No. 8.5 by 11 maximum. Okay. 8.5 by 11 maximum is the standard. What's that? So the actual length of it, I don't know because I haven't written it yet. But this is the practice test, and it would be a pretty good indicator. This one's 20 questions long. So, depending on the test, like some of our tests will require more calculations, and then there might be less than 20 problems. Some of them aren't really like aren't calculation intensive. It's like which one of these is quantitative versus qualitative. That's like a 30-second question if you know what quantitative and qualitative are. So this one might be a little longer than some of the other ones, but. Yeah, and it'll be open-ended, so these are not multiple choice. This is just the way it formats it. But and on the actual test, obviously, I give you room to do work or whatever. I wouldn't squish it all into 2 pages, but no point in wasting paper for a practice test. So you can go grab that and print it off. I don't bring printed copies. But any other questions about that? So you take a look at it over the weekend. Typically, the way I do it is we'll finish up most of Chapter 3 today. We'll do 3 and 4 on Monday and Tuesday. 4 is really quick. And then I'll do a review day on Wednesday, so you can come ask questions. Any questions you might have about the exam. All right. So, unless anybody has anything else they'd like to ask, we're going to move on. All right. So last time we were talking, we were learning about how to, calculate standard deviations, right? So we got into all this madness, right? So that was pretty fun. And came up with a standard deviation. I showed you another alternate formula, which we call the computing formula, which is also useful. It's actually, I was looking through your book. I don't think it's even in the book. I don't think. But this one's a little faster. If you want to use it, you could use it on the exam. And then it's also less prone to mistakes. Like I see people make a lot less errors on this calculation than I do on this calculation. And then the main difference is the main thing you want to also notice, and this will come up on your homework, is whether or not you're dealing with the entire population. So like if I'm just interested in students in this class right now, I could just treat you guys as a population because you're all right here. Versus if I'm just taking a sample of a larger group, it just changes the, basically all it does is change by the number you divide by. So sample is n-1, standard deviation, it would just be the whole thing. So in this example, we were treating it as a sample, so we divided by n-1, so 1 less than the sample size, right? But you could redo it, assuming it was the population. Luckily for us, we don't actually have to redo the whole thing, right? Because if I didn't do my thing here. I don't know why I left myself so much room. If you wanted to do that, it's just the, right, it would just be that sum of the x minus the mu's squared all over n in this case. But we already have this sum of all the squared deviations from the last example, right? It came out to be, what did it come out to be, 665.56? Yeah? In that last example. So we could just use that. And then instead of dividing by 8, though, in this case, we'll divide by 9. So what do you get if you take 665.56 divided by 9 and take the square root? The variability should go down a little bit, actually. Anybody got a calculator? Help me out. Nobody? We all have calculators, come on. It's Thursday? That's true. We should just have one day built in where we just don't do anything.
73.95.
And then square root that. 8.59? Or 599 or something? Yeah. Something like that. So it'd be like 8.6 if you rounded it, but I already wrote it down, so too late. Yeah, so if you notice, the sample standard deviation, right, was 9.12. If you assume you have your whole population, it actually lowers your variability a little bit, right? It'll make the standard deviation smaller, which it should, because now I'm not estimating the standard deviation anymore because I've actually observed my entire population. So this is the exact variability or standard deviation of this data set if you treat it like a population. Okay? Any questions about that?
So that would be if we're trying to find the sample.
Population. So assuming this is the entire class, right? So we're treating that and those 9 people as the population. Whereas in the last problem, assume this is a sample of a larger class. So with that case, that's why we did the n minus 1 rather than the n. So you'll run into it on your homework though, and you'll get it wrong if you use the wrong standard deviation. And then you'll wonder, why am I getting this wrong? I swear I'm doing it right. And then if you check, it's probably because you're using the wrong standard deviation formula. All right? Okay. Cool. So the properties of the standard deviation. So the standard deviation, it's always positive. Right? Because we squared up a bunch of positive values and we're taking the square root and we're only keeping the positive square root. If you have, the bigger it is, what does that mean? Bigger standard deviation means what? What does that say about your data if you have a larger standard deviation?
All over the place?
Yeah, it's more spread out. Okay. If you have a smaller standard deviation,
You have tighter grouping?
yeah, it's compact. So it's center. It's closer. Your data is closer to the mean. Right. Because remember, that's what we said yesterday. That was what that's what the standard deviation is actually attempting to measure. It's trying to measure how far on average your data is from the average, the mean. So the bigger it is, that's telling you got stuff all over the place, above and below the mean. If it's smaller, that's saying, no, everything is kind of piled up right in there around the average. Okay. And the other thing about it, though, is it is not what we call resistant. Right? We talked about this concept to outliers. Okay. The standard deviation, like the mean, is very, very, very highly influenced by outliers. Which is, in fact, even more so. Because remember, in the standard deviation, we talked about it yesterday, you end up squaring those deviations, right? So not only are you measuring how far away from it is from the mean, but then you're squaring that, so big numbers are going to be amplified. So if you have something that's way out there and then you square it, it's only going to get even bigger. So it's definitely not resistant to outliers. Okay. Cool. Then beyond the standard deviation, something we don't use quite as much, but it is used every once in a while in statistics, actually heavily, but not so much on a practical level. The variance of a data set, all it is it's just the standard deviation squared. Okay. Or I guess if you're talking about a population, it would be sigma squared. We're going to find out, though, the standard deviation is going to be way more useful to us than the variance. But it's a value that we use a lot. So there may be a problem or two on your homework where it asks you to calculate the variance. I actually already did this yesterday, the numerical summaries. I showed you guys how to calculate those in StatCrunch. So I'm not going to show you that. Well, we might come back to it to do some other calculations, but I'm not going to do that right this second. Yeah. So the variance is just it's literally the standard deviation formula without a square root in it. So it's just that sum of the x minus x bars squared over n minus 1, or the sum of the x minus mu squared over n, right? So it's the exact same formula, just no square root. The standard deviation is the square root of the variance.
Wait, minus what?
Mu? This is a mu. This one?
Yeah.
Yeah, it's a mu. It's like a Greek. It's like a little Greek m.
Why are we learning Greek in this class?
You know what? It's just tradition.
Is
square. Yeah. It's just what we've always used. I don't know. That's what we decided to use was Greek letters, and that's what stuck. All right. But I mean, I guess we could use M's and I don't know, O's or something. We could. But we do sometimes, right? There's an S, there's an X. Anyways, all right. That would be that one. Cool. Not that worried about the variance. Okay, so the standard deviation, one of the nice things about the standard deviation is it applies really nicely to normal distributions. And this is something known as the empirical rule. Sometimes people call it the 68, 95, 99.7 rule. That's what I call it. And the reason is pretty intuitive, actually. So if you have a normal distribution, what does normal distribution mean? What shape does a normal distribution have?
Oh, the bell.
Yeah. Say with mean, mu, and standard deviation sigma. Okay. This is what the empirical rule tells us. What does empirical mean? Does anybody know what that word means? To derive something empirically? Anybody know what that means? No? What is something, what does it mean to do something? There's a difference. It's actually sort of the contrast to theoretical. So you have some things that you can observe theoretically and some things you can observe empirically.
It's concrete.
Which one, empirical or theoretical?
Empirical.
Actually, it's almost the opposite in science. Theories are things that tend to be very well regarded as facts, right? Empirical things are things that are observed, actually. So if something is derived theoretically, so we can prove some things in math theoretically, right? We can prove that a certain number is an unbiased estimator of another. Or if we can't prove things mathematically, sometimes we can look at enough data that we can convince ourselves that it's true in most cases. And that's what empirical means. It means you derived it by observation. And so this empirical rule is not hard and fast. It's just something that's been observed over time with normal distributions. So you have this normal distribution. It's centered around the mean, right? That little mu. And the empirical rule says that if you go out one standard deviation from the mean, so if you go up one standard deviation and you go down one standard deviation, within one standard deviation of the mean, in almost every normal distribution, that will contain 68% of your distribution. So 68% of a normal distribution typically is within one standard deviation of the mean. Okay. Almost always, as long as your distribution is approximately normal. It then goes on to say that if you go out 2 standard deviations, so up 2 standard deviations, down 2 standard deviations, by that point, you've actually covered about 95% of your entire distribution. So in things that are normally distributed, almost 95% of the population is going to be within 2 standard deviations of the mean. Right? That's the nice thing about normal distributions. It's nice and lumped up around the mean. It tapers off pretty quickly out on the tails. So by the time you go out 3 standard deviations, so down 3 standard deviations, up 3 standard deviations, by that point, you've covered, what do you guess? 99.7% of your data. Now you know why I call it 68, 95, 99, 7 rule. Okay. So the standard deviation can actually give us some pretty quick information about the spread of a normal distribution, just using the empirical rule. All right. So let's see. Let's look at some ways that could be applied. We're going to get very familiar with drawing nice bell curves. Do that a lot in this class. So math scores, for example, on the SAT. So standardized scores are typically built to intentionally produce normally distributed scores. So the math scores are no different. They have a mean of 515 points and a standard deviation of 114 points. So what percent of SAT scores are between 401 and 629? That's the question. So normally what I do with these is I kind of draw it out. You might be able to do the calculation in your head, but I usually just start at the mean. So the mean is what, 515? Right, that's the average SAT score. And so I go out and mark my standard deviations. Okay, so if you go up one standard deviation, what's going to be this value right here? So the mean is 515, right? So this is mu. This is sigma. So what would this number be up one standard deviation?
6.9.
Yeah, so you add it, right? So you take a mean and add one standard deviation to it. That would take you up to 629. And similarly, we could go down standard deviations. If you go down standard deviations, what does that take you down to?
Probably 401.
Yeah, I think it will. 401. You could draw some more here values. What do we got? If you add another 114, what do you get? 743, I think. 743 plus 114, that's going to take you up to what? 857. So I'm just adding 114 each time. Going down, subtraction is hard. What is that? Is that 287? If you take 401 minus 114, does that work? Yeah. And then go down from that is what, 173? Yeah. Subtract. Okay, cool. Yeah, so now the question is what? Between 401 and 629, so where is that? That's right here. Yeah. And so how many standard deviations is that? That's one standard deviation above and below. And so that's how much of our data?
68.
Yeah, so the answer here is about 68% of all test takers are going to score between a 401 and a 629. Yep. Make sense? Okay. All right.
So you went down that way, just
By
subtracting 114?
Yeah, so each one is 114 less than the other. I think, unless my mental math is incorrect. But
And then that way you added 114?
yeah, I'll get you a second. Bobby, you had a question?
Is it always going to be like a percentage on the rule? Like, is it always going to be like 60?
For the empirical rule, yeah. For the sake of us right now, it will. We're going to learn later how to handle it when our values don't lie on these nice cutoffs.
Okay.
Yeah, we'll deal with that later. It'll be tons of fun. Yeah, question back there.
So is it always the mean minus the standard deviation?
Yeah. That's how you're always going to get these tick marks. Yeah, is you're going to go up by the whatever the value is and down by the value. Okay. So let's try another one. So they're not always. They're always. What range is going to cover 99.7% of all SAT math scores? So you go back to your diagram from before, right? So to cover 99.7, how far out do you have to go? I need to go out 3 standard deviations both ways, right? And to do that, how far up do we have to go and down? We have to go down to 173 and up to 857. So I'm just taking those numbers from the last chart. I'm not going to redraw all of them. Okay, but that would be the answer. Okay, so 173 up to 857. You would not expect to see hardly anyone below or above those numbers. It's possible, but you're not really going to see it. Okay. All right. They can be a little more complicated than that. So, for example, what if I wanted to know, so my drawings are getting worse. I'm getting lazy. What if they wanted to know, say, between, so here's 515, the next one was 629, the next one was 743, the next one was, what, 857? And they want to know what percent is in here. How could you solve a problem like that?
4, and then it should get 3.
Ooh, careful. I think you're getting on the right track. I'm gonna get rid of that 515. It's not really necessary.
Half the difference between the 68 and 95.
Why?
Because that was the increase.
Oh, I see.
So you said take 95 and subtract 68?
And then divide it by 2.
Okay, so that would be what, 27? And then divide that in half?
So 13.5.
Is that true? Do people agree with that or not agree with that?
Good. Sounds good.
Why would you do it that way? Does anybody know? Can anybody see why they did that way? Why did you do 95 minus 68? Because it makes sense. Dang it. Not necessarily to everybody, right? So you go. So think about this, right? I need some colors or something. And you guys claim you can see my colors, so I'm going to believe you. Okay. Look, this is 95 from here, right, to here. That's 95% of the data. Okay. You see where we're going with this? Well, some blue. Blue is cool. This is 68% of the data, right? So if you take 95 minus 68, what does that give you? It gives you this chunk and this chunk. But we only want one of those, so what do? We divide it in half. Yeah. Is there another way we could have got that?
So can't you just divide by a quarter?
Can't. No, not quite. 95 by a quarter? Try it. It won't work. It won't work actually. Yeah. Because notice these aren't equal size chunks, right? These two are bigger than those two. Yeah. The other way some people will reusing it is they'll just start dividing it up. Okay. So it's like if this is 68 right here, right? Then this has got to be 34 and 34. And you can just reason your way out. So now that you've covered 68%, well, you go out another, that leaves you with 27. So this has got to be 13.5. This has got to be 13.5, right? There's very little left out here because you got 95% and now you're going with 99.7%. You only have 2.7% to split out there. So this is something like 1.35 or something. And then out here you have like nothing. It's like 0.015 out here. You can get those numbers like that too. Just start dividing your percentages out and say, oh, that's this chunk, that's 13.5%. So either way. Okay? This is something we're going to do a lot more later, like taking big probabilities or big percentages and subtracting out smaller percentages or whatever. We'll see. We'll come back to that. All right. Cool. Any questions so far? So far, so good? All right. So the empirical way is a quick way to use those standard deviations to help tell you things about a distribution. Another way that we're going to use that standard deviation is in calculating measures of relative standing. There's two basic measures of relative standings that we're going to use. One you are probably familiar with. Those are things called percentiles. The other thing we're going to be using is something that we call a Z-score. And Z-scores are associated with normal distributions. Percentiles can be, but Z-scores are specifically for normal data. All right. So we're going to go into both of these a little bit. All right. So first I want to talk about the Z-score, and then we'll come back to the percentile. So the way we calculate a Z-score, so first I'll give you the formula. Okay. We call it a Z-score because the variable we've always used for it is a Z. Okay. And to calculate a Z-score, you're going to take the opposite. You're going to take a number minus the mean and divide by its standard deviation. Okay. So this would be, for an observation X coming from a population or from a normal distribution. With a mean of mu and a standard deviation of sigma. Okay? So to calculate an observation z-score, first you subtract the mean, then you divide by the standard deviation. Sometimes this is also called a standard score because you're standardizing that difference. So notice the numerator is just the observation minus the mean. That's just a deviation, right? That's how far above or below the standard, the mean it is. Then what we do is we divide by the standard deviation, and we're basically sort of scaling it down to figure out how many standard deviations above or below an observation is. So that's what I'll write here. So what does it actually measure? It measures how many standard deviations above or below mu x is, right? And so notice if z is positive, then x is above average, right? And if z is negative, that means x is below average. So like so many things in this course, the easiest way to figure out how you do it is just to see it calculated, all right? This is conceptually what it is, but it's really not that difficult to calculate. So I'll give you an example here. So let's go back to the SAT scores, for example. Okay, so the SAT scores, they have that normal distribution with a mean of 515 and a standard deviation of 114. And I want to find the z-score, say, for a student who gets a 580 on their math test. All right? So in this case, what is my x? What's my observation that I'm interested in? So z is what I want. So the idea is the z-score has to be the observation minus the mean over the standard deviation. Yeah? Okay, well, what is the observation we're interested in here? Yeah, so x is 580. That's the person we're interested in, right? What is mu here? Yeah, so the mu is the mean, 515. What's the standard deviation of SAT scores? 114. Okay. All right. And so here, to get our z-score, we're just going to be plugging in the observation minus the mean all over the standard deviation. Okay, so it's 580 minus 515, so that's what, 65? And then 65 divided by 0, or 65 divided by 114, what do you get? We'll round it to 2. Z-scores are typically rounded to 2 decimal places. What do you get? 0.57? Yeah.
So how do you determine the x again?
So the x is whatever observation you're trying to find the z-score for of. So this one case, it's a student who scored 580 points, so that's our observation. The mean and the standard deviation are fixed. The mean for this would always be 515, the standard deviation would always be 114. The only thing that's going to change is the scores we're interested in looking at. Okay, so this would be their z-score. How would you interpret that? What is that actually telling us? They are above average. How far above average? Standard deviation. They're not 57% above average. It tells us that this student, not student, student is 0.57 standard deviations above average. That's what a z-score tells us. So honestly, it's like if you think about a normal distribution, that person is still within that one standard deviation range. This person's pretty common, right? Not to like knock on them or anything. They're still above average, but they're a pretty common observation. They're still within one standard deviation of average. Okay. And so what you start to see though is that as those standard deviations start to get big, or as the z-scores get big, that's telling you that these people are starting to get further away from average. They're sort of becoming more exceptional either at the high end or the low end. So z-scores of under 1, z-scores in the 1, those aren't that big. If you start seeing z-scores like at 3 and above, that's pretty exceptional. Because we know, right, from the empirical rule, by the time you hit 3 standard deviations above or below the mean, you've already covered like almost your entire population. So anybody that's more than 3 or less than 3 below, or more than 3 below, those people are pretty exceptional in some way, whether good or bad. Okay. How about a person who gets a 390? Same problem, right? So what's the only thing that's going to change here? Yeah, so we'll change our sign on the z-score. For the actual formula, though, what's the only thing that changes? The x is the only value that changes. So now we're talking about a student that's scored 390 and has a standard, but the mean and the standard deviation don't change. And what do you get for that? Was that a negative 125 over 114? What do you get, negative 1 point something? 1.09? Anybody else get that? All right, cool. So that would be their z-score. So what does it say about this person? Yeah, they're just a little bit more than 1 standard deviation below average. That's still not that crazy, right? You know, most of your data is right there around the 1, 2 standard deviations around the average. This person is pretty common, or their score is pretty common still. All right. It is below average, yeah. So this student, I'll write it here, is 1.09 standard deviations below average. Yeah. Yeah. Okay. All right. Above average positive, below average negative. Which one of these students was further from average? Which one of them is more likely? What do you think? Which one of these do you think is more likely to be observed, actually? Yeah, so even though the 580 is above average, the 580 is closer to the mean, which means that it's more common. In a normal distribution, at least, right? So it's more common or more likely to occur. The 390, on the other hand, was further from the mean, so it would be less common. You're more likely to see someone around a 580 than you are to see someone down around a 390. That's basically what it means. Later on, what we'd like to be able to do is maybe put some sort of, I don't know, guess about how likely exactly you would be to see people there. But for now, we'll just stick with what we got. Okay? Cool. So the bigger the z-score, the more exceptional those people are becoming, for better or for worse. Okay. All right. The nice thing about z-scores is they allow you to compare two normal populations that might not have the same mean and standard deviation. So a classic example is like trying to compare someone's SAT score to the ACT scores. Some universities will take both. You could submit one or the other. And so you need a way to compare people who took different tests. So the SATs have that mean of 515 and 114, but the ACTs are on a totally different scale. The ACT average score is only 20 points, but their variability is only 5 points. Okay, so then two students walk into admissions. Jack has a 650 on the SAT. Jill got a 28 on the ACT. Are they both above average? Yeah, they're both above average, right? The question is, okay, if I just have to make a decision and these two students are equal in all other respects, which one did relatively better on their test, right? So that's what we want to know. And the key to doing that is you're going to calculate their z-scores to show how they did relative to the rest of their test takers, and that's going to give you an idea of which one did better. Okay. So for Jack, he was taking the SATs. He got a 650 on a test with a mean of 515 and a standard deviation of 114. Okay, so what was Jack's z-score? About 1.18. Okay, it's pretty good, right? He's more than 1 standard deviation above average. If you go over and you look how did Jill do on hers? She scored a 28 on a test that had a mean of 20 and a standard deviation of 5. So what is her Z-score? 1.60? It's exactly 1.6, isn't it? Yeah, 1.60. So who did relatively better? Yeah, so it looks like even though they were both above average, compared to other test takers, Jill actually outperformed ACT takers more so than Jack outperformed ACT takers. Yeah? So that's another advantage to talking about measures of relative standing. So they help tell us where they are relative to their population. All right? Pretty straightforward? Cool. Hold on. Go too fast. You're not writing down all the stuff, are you? You are writing down all the stuff, aren't you? You can get the slides.
It's too much work to go back.
Yeah.
It's too much work to go back later on.
Oh.
So might as well.
Yeah. Yeah. Question?
Yeah, the slides are just on your recording, right?
No, I save them. Like you can download the actual like annotated slides, like these filled-in slides that you're seeing right now. Yeah, I download them, and you can download them. What's that?
My math lab, right?
Yeah, they're right here on my math lab. Go to course documents, annotated lecture slides, right? And if you look at them, like these ones are not up to date because I just filled in a bunch of junk. But if you open them, it looks just like the slides that we just did, right? It has all the filled in stuff. Yeah, you can get those. Okay. Good question. Cool. Everybody feel like they can calculate a z-score? I think you can all calculate a z-score. So the other one we were talking about is percentiles. What does a percentile measure? What does that mean? So let's say to be in the, say, kth percentile. What does that mean if you are in the kth percentile? So if you're in the 80th percentile, what does that mean? You're among 80% of the sample? You're actually among 100% of the sample.
You're above.
Yes.
Yeah, you're above.
Yeah. Yes, you're above 80% of the sample. So like if you're talking about SAT scores, if you score in the 80th percentile, that's pretty good. It means you outscored 80% of students who took the test, right? So to be in the kth percentile means an observation is at or above k% of a population. So if it's something you want to be good at, you want to be in a high percentile, obviously. If it's something you don't want to have high scores on, then maybe you don't want to be, right? Okay. So there are some examples of percentiles, I think, in your book, but we're actually going to concern ourselves more with specific percentiles, and we want to talk about the quartiles. Okay. So typically the quartiles, we split our data up into quartiles. So we'll say we call Q1, that's the first quartile. And if you're splitting your data into chunks of 25%, to be on the first quartile, what percentile do you have to be on? What would that be? So splitting your data into fourths is the same as splitting it into what percentages? 25%. Yeah. So the first quartile, we call that that would be the 25th percentile. Okay. The second quartile, so I went 25%. If I go another 25%, what would that be? That would be the 50th percentile, but we actually already have a name for that. What do we call that? We already have a name for the 50th percentile. It's the point where 50% is below and 50% is above. We call that the median. Right? Remember, you line your data up from biggest to largest, and you just pick the value smack dab in the middle. Boom. Yeah, that's the 50th percentile. So we call that the median. And then Q3 would be what? That would be your third quartile. So what percentile would that be?
75th.
Yep. Yeah. Okay. So these are the quartiles, but we don't call the median Q2 because we already have a name for it. All right. Finding them is just as easy as finding the median, right? So finding the median is not particularly challenging, and finding the quartiles really isn't either. So I'll give you some numbers here, which happen to be in order, so that's nice. We don't have to go order this junk. This is a sample of 18 collision coverage claims, right? So you get in an accident, and then you go get your car repaired. You have to make a claim on your insurance, and this is how much it costs to get it repaired. So this was 18 of them, and I listed them in order for you. So find the first and third quartiles of the claim values. So to find the first and the third quartiles, you actually have to get the median first, and then you can go grab the quartiles from there. Okay. So what is the median of this data set? So if there's 18 claims, then where's the median going to be? 1, 2, 3, 4, 5. Yeah, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so there's no actual true median. So what do we have to do? Yeah, we have to average those, right? 1805. Okay. Anybody else get that? Is it 1805? Okay. So the median is right there in the middle. It's 1805. So now, if I have my data split in half, then where do you think quartile 1 would be? Yeah, all you do is you just take the bottom half of your data, stupid menu, right? And you find its median. So if there's 9 observations there, 1, 2, 3, 4, 1, 2, 3, 4, it's just going to be the median. So the quartile Q1 is just the median of the bottom half of the data. So that'd be 735. And then Q3 is just going to be the median of the top half of the data. So 1, 2, 3, 4. 1, 2, 3, 4. It's 4668. Right? So it's just the median of the low half. And this is just the median of the top half. So, right? Make sense? So you find your median, split your data in half. Median of the low half is Q1, median of the top half is Q3. Pretty easy? Cool. All right. So one measure of variability that we use. So I told you standard deviation isn't always really the best measure of variability because it's really sensitive to outliers. So one measure we use that's robust against outliers or resistant to it is we look at the interquartile range. And what the IQR is, we abbreviate it as IQR. It's just what's the range from Q3 to Q1. And what it really is it's kind of like the range of the middle 50%, right? Which could be informative because you assume that in any distribution, the middle 50% are probably a pretty decent representation of the population as a whole, okay, unless you just have some weird distribution. And so one thing you might think is, okay, maybe the data is way spread out because of outliers, but let's see what the range of that middle 50% is, because that's who I'm really concerned with. You know, those more common observations. So all you do is you take Q3 minus Q1. Not too bad. All right, so like for the data we just did, if I wanted to take that, right, then the IQR would be, what was our Q3?
4668.
Yeah, so Q3 is 4668, 735. You just do the subtraction. 4668 minus 735, and what do you get? 3,933. Yeah. Okay, and it's in dollars. Right? So the interquartile range is just a little under $4,000. So that says, that kind of gives us sort of a spread of those middle 50% of claims. It says that the middle 50% of claims, they only cover a range of about $4,000. So that's not super spread out. I mean, right, that's not particularly variable. But we do see there's some weird stuff happening. Like some of these claims are really huge, right? So that these would be probably totaled cars or something like that. And so one thing we can also use the IQR for is we use it to test for outliers. All right. So for the tests for outliers, what we do is we sort of we establish some boundaries. And what we're trying to do is we want to basically establish some boundaries that we think are a pretty reasonable area to see data in. So to get our lower bound, we go from Q1 and we go down 1.5 IQRs. And to get our upper bound, we go from Q3 and we go up 1.5 IQRs. Okay, so it's like we're going to go from Q1 and go down a little ways. We're going to go up from Q3 and go up a little ways. And then what we look for is we look for any observation either below the lower bound or above the upper bound. And if we find anything out there, we flag those as a potential outlier. Okay. So we basically make like a fence. And we say this is the bottom of the fence and this is the top of the fence. Everything in there is cool, but if there's anything outside that range, then we're going to flag it and be like, that looks pretty uncommon. Okay? And again, this is something that was derived, this is something that we came up with empirically. We just found it was over a lot of data sets that it was a really good indicator or a really good test. Right? It's not like there's any sort of like theory that tells us you should do it this way. It's just looking at a lot of data. Okay? So, last thing, we'll do this. Let's do it for our data, right? So, because we already have all these numbers for our car claims. So to get we want to go ahead and get our bounds. So to get our lower bound, we're going to go from Q1 and subtract 1.5 IQRs, right? So that's going to be, Q1 was what, 735? And we're going to subtract off 1.5 times, what was our IQR, 39 something something? 3933. Okay. So what is 1.5 times 3933? It's big. It's like 6,000 or something like that. 5899.5. 5899.5.
Yeah.
So this is actually going to give us a negative number, like way negative, right? Like negative 5,000 and something. What is it? 735 minus that.
Negative 5164.5.
Are we going to have any observations that are lower than negative 5164.5? No. Sometimes your lower bounds or your upper bounds might be way out of range. I mean, because our claims are obviously bounded by 0. So we're definitely not going to have anything on the low end that's going to qualify as an outlier, but we do want to still check the high end. Because if you go from your upper bound, so that's supposed to be Q3 plus 1.5 IQRs. Okay, so that's going to be, Q3 was, what number was it? 9908? Right? Wasn't that our Q3? I think it was.
4668.
Oh, it's 4668. Yeah, I'm making stuff up. It's 4668.
So confused.
There you go. 4668. Right, we got it from our data originally. And then we're going to add that 1.5 times QR. We already found what that was. We're going to add that 5899.5 because we already calculated that. And what do you get as your upper bound?
It's 10567.5.
105, 110.
10,567.5.
And that's our upper bound. Does anything exceed that? Yeah, notice that this claim, this $21,000 claim, it exceeds our upper boundary. And so this is the value that we would flag as a potential outlier. You know, because basically what we said is that we wouldn't be surprised to see claims anywhere from like basically negative or zero up to 10,567.5. But this one is way out there. This is way above our upper boundary. So you might want to look into this one. Is this really actually representative of claims? You know? Okay. Okay. Cool. I will see you on Monday.